So in this video we're going to look at trying to do the Laplace transform of this function here, k times the exponential function to the power of a times t. Now here our k is an integer, our a is an integer, and t is a function of time. Now it doesn't have to be time, it could just be a parameter that you want to use, but in physics t would be a parameter of time. So the Laplace transform. So our setup is our Laplace L, our function, which is a function of t, which is what we want here, and then that equals the integral from 0 to infinity. So this is the unilateral version of f of t multiplied by an exponential function to the minus st, and with respect to t. Now s is our parameter, which can be real or complex. So s is the parameter, and there's a rule for this parameter that it must be greater than 0. So I'm going to write here s is greater than 0, because if s was less than 0, this would be a positive in our indice of the exponential, in which case this integral here could diverge. We want this integral to converge. That's what we want, i.e. from 0 to infinity. Okay, so now let's do our setup with our function. So our Laplace L of k times e to the at, that equals, range of integration stay the same for this function, and f of t is just this, so k e to the at, and then our integration here is with e to the minus st dt. So the integral result for this will be our Laplace transform for this function. That's basically where we are trying to aim, and that's our goal. So now let's just simplify this off so we can integrate it. So the k is just a constant, so that can come out front from 0 to infinity, and now we've got e to the at, e to the minus st. So we can use the rules of indices here. So put in my e. Now just to be careful here, we don't want a positive value in our integrand here. We want the negative value for our indice. So if I put a negative, and then as we're integrating with respect to t, I'm going to factor out the t, and then I'm going to get some result in here with these two terms. So I've got a minus t here, so I'm going to put my s there, so that would take care of my minus st, and then I'm going to need to subtract a, because minus t times minus a will give me positive at or ta, whichever round you want to go. So that's my setup for my integral, and then dt. Okay, so now to integrate this, we're just going to do a u substitution. So let u equal this part here. So let u equal t times s minus a, and then usual u substitution rules. Du equals, well, the derivative of this with respect to t is s minus a, and then that's dt. So therefore my dt equals du divided by s minus a. So let's set this up into our u variable. So k, 0 to infinity. Now our parameters here are going to stay the same, so we don't need to change those, because if t is 0, our u is 0. If t is infinity, our u will also be infinity. Now one other rule we need to be careful of here is s minus a. So our s must be greater than our a. So I'm going to write that here, s must be greater than a. Otherwise we'll have a negative term here, and then this integral then will diverge. So we want this to converge with s greater than a. Okay, so now e to the minus t s minus a, that becomes e to the minus u, and then my dt is simply this. So du over s minus a. Okay, just a little bit of a simplification here. My s minus a I can bring out the front. If I'm integrating with respect to u, this is just going to become a constant. So if I take my s minus a out and cross that off. So now I'm ready to set up my integral and find the result. So e to the minus u. Well, if I integrate that, that's pretty straightforward. That's just negative e to the minus u. So that's the result of my integration. So k divided by s minus a. and then I'm going to multiply that by negative e to the minus u, and then my parameter 0 to infinity is where I'm going to calculate this from. Okay, so we can put our result in here. So what if u is infinity? I've got negative e to the negative infinity. Well, that is just going to be 0. And what about for 0? So negative e to the negative 0, that's just going to become, well, e to the negative 0 is just e to the 0, which is 1, and my negative, that's negative 1. So therefore now my result is k over s minus a, and then I've got 0 minus minus 1. Okay, so now that will just cancel out. I'll just have a 1 here, and that will be the result of my integration. So now I'm going to put my result up here, and we're going to find some examples of the exponential function transformed at different values for k and for a. Okay, so my result I got earlier was k of s minus a. Now that was my Laplace transform for my general values of e to the at. So this will work for all values of the exponential function. So now let's be a little bit more specific, and let's have a look at, let's say for example, 3 times e to the 4t. So my Laplace transform of that, my k is going to be 3, and I'm going to have s minus a. Well, s is my parameter, so that's going to stay. And here my a is just positive 4. So that's an example there for those values. Now let's have a look at another one. What about the Laplace of pi times e to the 2t? So again, using my general formula, that equals pi, that's my k, and then s minus my a, which is 2. So that would take care of that one. Now what about if I've got the Laplace of 3 times e to the pi t? So using my generic formula again, using this, I've got 3 over s minus my a, which is pi. So s minus pi. So there's some examples of Laplace transform for the exponential function k e to the at. Okay.